Okay. Okay, let me start. Good morning, everyone. I am Kunmo Koo, postdoc research associate at the EPIC facility of Nuance. And today's tech talk will be about the graphene liquid cell TEM, which is the method for high resolution imaging of materials inside of liquid using the TEM. In today's talk, I'm going to briefly introduce about the GLC technology and go through the practical method for making and observing liquid with the GLC and give you some examples. Liquid phase transmission electron microscopy is not an unfamiliar skill anymore among the material scientists and the biologists recently. Conventional light microscope is a very good tool for live imaging, but the resolution is kept to several hundreds of nanometers, which is sometimes not sufficient for resolving many reactions. On the other hand, conventional and cryo-electron microscopy is a very robust tool for imaging static structure of molecules and crystal in very high resolution, but the imaging of native reaction inside of the liquid is not capable. Although there is some limitation, liquid TEM method is by far one of the most powerful tools for imaging live reaction occurring at the liquid in decent amount of resolution with TEM. For placing of liquid inside of the microscope, there are several ways, but the easiest way is to put your soaked sample directly into the scope. Of course, in many cases, it will not going to work, and the facility manager in most locations, including us, will not allow to do this, since there is a risk of contaminating the holder and the microscope. The example shown here is using super low vapor pressure ionic liquid, which does not evaporate under the TEM vacuum. As you see, using the STM tip biasing holder, one side of the nanowire is stick to one electrode and the other end is contacted to the ionic liquid, which is deposited on the cathode material. Upon the bias, the volumetric expansion of the liquid of the nanowire by intake of lithium is well imaged with the TEM. Again, to do such experiment, your liquid must have extremely low vapor pressure, so should not go away under the TEM vacuum, which is about 10 to -5 to -6 Pascal. Therefore, the applicable liquid is highly restricted to some special liquids. Most of the aqueous solution, organic electrolyte, or biological buffer, which you might have interested in, will not work. That is why you need an aquarium inside of your TEM chamber to observe a liquid in most cases. There are many encapsulation methods for the liquid, including the MEMS-based silicon nitride cell and 2D material encapsulations. I would like to compare them one by one in the chronological orders. The modern MEMS-based liquid EM is attempted around early 2000 with the silicon nitride with the liquid channel form inside. With this method, 5 nanometer of spatial resolution could be achieved. In late 2000s, commercial silicon nitride cell holders from many vendors with regional dimension and material came out. Using the holders, liquid cell microscopy became accessible to many users since it is relatively easy to prepare and safe compared to the previous methods. However, the intrinsic problem of thick nitride and thick liquid due to the bulging effect limits the achievable resolution to around 1 nanometer. To overcome the resolution limit of the nitride-based cell, in year 2012, graphene liquid cell is developed. In this method, small amount of liquid is hermetically sealed in between 2 layers of single-layer graphene by van der Waals force. Since the thickness of both membrane and the liquid is very small, atomic resolution imaging was enabled. By using the graphene as an encapsulation instead of silicon nitride, we can expect 4 major benefits. First, graphene is physically robust and theoretically impermeable to every atom bigger than a proton. So it provides complete isolation of your liquid inside of the vacuum chamber. Secondly, it is highly transparent to the electron since it is composed with very light carbon atoms and it is only 1 layer. So additional scatter from the membrane become nearly negligible. Third, graphene is to be known as a good radical scavenger. Water is very easily break down to the reactive oxide species when it is hit by electron. So there are always many unwanted radical species generated in the illumination area. These radicals can intervene to your reaction or damage your sample. graphene consumes nearby radicals and transforms to graphene oxide, so the radical effect is reduced at the graphene liquid cell. Lastly, graphene is good conductor of heat and charge. Therefore, the imaging artifact and drifting from the electron charging can be minimized. Actually, there are many different techniques for the graphene liquid cell. One is the templated one, which helps you to localize your liquid pocket easily, because the liquid pocket in the conventional GLC is not usually randomly generated. And the other one is the chip-based one with the liquid flow capability. Those are very good methods for overcoming the practical limitation of simple graphene liquid cell. However, they require special chips and materials. I think those methods are a little bit tricky for the liquid EM starters. Today, I'll mostly focus on the very first technique, which is non-templated or supported one, and the just simplest graphene liquid cell for rest of my presentation. So how to make the graphene liquid cell? Before we going on, I would like to recommend you to watch movie from the Jove article, which is published by one of my former colleagues. This movie has pretty much everything for the GLC process from the scratch, and this talk today will cover the same method in detail. First, for the material, you'll need a graphene, of course, and the quantifoil grid for the support, and the copper etchant and your material for making the liquid cell. The graphene here is preferably from the CVD grown single layer graphene rather than exfoliated or reduced graphene oxide, because high quality graphene with less defect and big grain size will increase your success rate. Also, for the supporting perforated grid, I recommend you to buy C-flat grid from the vendors with gold grid bar, since the copper grid will just etched away with the etchant. These grids are originally used for the cryo-TEM support, but they are also good for the graphene support since it has very smooth and good adhesion with the graphene. For the small tool, you'll need a small platinum wire loop. You can either buy one or make it with the platinum wire. This tool is to pick up the graphene or grid floating on the water with the surface tension. Also, this tool needs to be corrosion resistant because it will be submerged to the corrosive etchant. First step is to attach a graphene to your grid. We use gold quantifoil grid for support. It has a smooth perforated carbon film on the grid bar. In this grid, we have two sides. There is shiny gold side and darker rainbow-ish side, which is a film attached side. We have to put graphene on the carbon side for the good adhesion. Then we need to cut the graphene on the copper foil and make it flat with the slide glass by squeezing it, and place the grid upon it with the carbon film side contact to the graphene. And drop small amount of isopropyl alcohol on the top, and it'll make them stick together with the capillary force. If you have some trouble with the adhesion, maybe your grid and the foil is not flat enough, or grid is maybe contaminated and not in a good condition. Optional liquid suction can help them stick together by removing IPA from one side, but in most cases, you don't need it. And then float your stick graphene foil together to the etchant solution to remove copper out of your graphene. That is why we are using gold grid rather than a standard copper one. In this process, we use ammonium persulfate solution, which is around 1.1 to 0.2 molar concentration. It'll etch away copper quickly when it is heated around to 40 degrees Celsius. Other etchants, such as ferric chloride or sodium persulfate, can also be used, but they will contaminate your graphene surface with the metal ions. Liquid cell containing other ions, such as iron or sodium, is sometimes very annoying because they are also participating to your reaction or nucleate upon the electron beam irradiation. After removing the copper from your grid, pick up the grid with the platinum loop and place it onto the clean DI water for rinse. Later, pick up your grid from the water and dry upside down to remove moisture from the graphene transferred grid. Now you have graphene transferred grid. There are several ways to make a simple graphene liquid cell with your transferred grid and the graphene. The easiest way is to put a small amount of liquid on the top of the graphene grid and cover with another graphene grid facing graphene side together. If you have very bad luck, your grid bar will crossing each other and your visible area will be very small, but usually there is some good area on the grid. If your liquid is not wetting on the graphene can delaminate it and slip away. This is happen when you are doing with the aqueous solution because graphene is generally hydrophobic. In this case, increasing viscosity will help a little bit. Another method would be the scooping graphene method. This method is generally good for trapping aqueous liquid inside. You can pick graphene from your liquid and pass through the loop upon the graphene grid. It'll generally yield a lot of wrinkled graphene on your grid, but aqueous solution can be more easily prepared and compared to the imposing grid method. This is an example of GLC-made scooping method. You can see many wrinkles on the graphene, but in between the wrinkles, there are liquid and nanoparticle entrapped. Moving at the right side is the electron beam-induced etching of the gold nanoparticles with halogenide ion inside of the liquid buffer. This is formed from the scooped graphene cell, and you can clearly see the fringes from the lattice of gold during the etching reaction. With completed GLC, you can just use conventional single tilt or double tilt holder, but there are always another option like cryotransfer holder or heating holders for your reaction. This is because your sample is same size of the standard 3mm grid rather than big silicon chips. Using the cryo holders, you can see the phase transformation of water to ice or other reactions that slows down at the cryogenic temperature. For a heating holder, you can apply moderate heat to your liquid cell to see etching or nucleation reaction happening inside of the liquid. Let me finish on my talk with giving some examples of GLC application in the real research. First application I would like to introduce is about the crystal growth and the nucleation. Since we can achieve very high temporal and spatial resolution in the liquid, we can see the early stage of nucleation and growth of nanoparticle in detail. This work is first paper reporting the graphene liquid cell published in Science. In this work, platinum salt precursor solution is encapsulated in the GLC and reduced with the electron beam. They have observed non-classical growth of nanoparticle by coalescence at 1-on-1 plane, which is less covered with other molecules. Second application for the graphene liquid cell is the battery experiment with the TEM. With the GLC, it is relatively hard to make a circuit since the graphene is conducting and pocket is very small. However, we can induce chemical lithiation with the electron beam illumination, which is similar to the actual battery charging mechanism. With this setup, many researches are done with the volumetric expansion and the degradation, and the orientational preference for the lithiation, and development of solid electrolyte interface layer, and the crystallographic study during the alloying and the dealloying stage of the charging. Last example of GLC I want to introduce is imaging of wet biomolecule with the electron microscope. Of course, you can also do this with the cryo-TEM, which is very reliable and robust method for resolving structure of biomolecules. However, with the GLC, you can get some different information from their pristine hydrated condition. For example, the figure from the left side is the image of the ferritin, which is iron-bearing protein. Also, since it is not frozen, a molecule inside of the GLC pocket can move freely. Therefore, we can also observe the movement and live reaction of the biomolecule. These are the selective list of the article about preparing the graphene liquid cell. The first 2012 Science paper is the first paper that developed graphene liquid cell that I have introduced in the past slide. The second one is good visual guide for making the graphene liquid cell. And third one from the nanoletters suggest various strategies for preparing GLCs. And last two papers are introducing another type of graphene liquid cell, which is capable of liquid flowing with MEMS fabrication technique. And I have got some answer to your questions from the participant yesterday in this slide. First question was the volume of the liquid pocket. The answer is about few attoliters, which is 10 to the minus 18. You can consider a typical area of the thickness of the liquid cell in several hundreds of nanometers. Second question is about the radiolysis. I guess this question is from some experienced liquid cell user. Unfortunately, there is no way to completely eliminate the radiolysis unless you stop the beam. I think a more important thing is to keep your radical concentration below the threshold. The concentration of radical can be controlled with your electron dose because the radical have a short lifetime and also the diffusivity. And also, adding radical scavenging species such as graphene and alcohol will help your radical concentration reduced. Third question, I think I have explained in the past slides, but you can also refer to the video journal in the future. Last question was how to avoid folding of graphene. This is very hard thing to do because graphene is very flexible. Generally, scooping freestanding graphene will incorporate a lot of wrinkles, and direct imposing of two transfer grid will yield less wrinkles. To achieve wrinkle-less transfer of graphene, you might consider coating some polymer upon the graphene before you etch the copper, but it is sometimes very tricky to eliminate polymer completely after the transfer. The best thing you can do, in my opinion, is to use highest quality graphene you can get with a very large grain size and low impurities. For removing of contaminants, you can float your graphene longer and several times to warm water to rinse the contaminants. Okay, thank you for your attention. And if you have any question, please let me know.
Yes, if you have any questions, please feel free to mute yourself and ask, or you can put them in the chat.
Hello, it's a very good talk. Thank you. Actually, can you add some applied bias to the actual liquid cell?
You mean the bias in the GLC?
Yes.
Actually, to do the biasing, we need some circuit. I mean, the cathode and the anode. But in the GLC, graphene is a very high conductor, a high electron conductor. So it is very hard to form exact circuit on your material. So instead, we can do the lithiation reaction with the electron beam.
Okay. And how much then actually electron dose anyway make some electron dose into the actual sample? Can you then measure that?
So you can refer to some reference papers for the exact electron dose, but normal dose for the GLC image is somewhere between the 1,000 electron per angstrom scale per second to 10 to 4 or 5 electron per angstrom scale per second.
Okay, great. Thank you very much.
To compare the result.
Hi, Kunmo. This is Nikolai Moldovan. I have a question about what would be the pressure and temperature in these cells during observation?
For the pressure, I don't have an exact number because there is some argument between some researchers because about the pressure, because the van der Waals between a force between two graphene layer is some people are saying is causing a pressure buildup inside of cell, and other people say that that amount of pressure is not really big. But actually, we don't know exactly what is the pressure inside of the graphene liquid cell because there is no way to measure the pressure inside of tiny attoliter sized graphene liquid cell. But in my opinion, it is not very high and somewhere around between our atmospheric pressure, because some pressure related reaction like nucleation is not very different from the outside experiment. And for the temperature, the temperature is not really high, because if the temperature in the GLC is very high, you cannot see the liquid inside because it'll evaporate really quickly. Because graphene liquid cell we use graphene, which is very good conductor of heat, so the heat will dissipate really quickly. So I think for the temperature, it is around the room temperature, but still we can use the heating holder or cryo holder to control the temperature a little bit precisely.
Yeah, I believe there was a question in the chat as well.
Yes, resolution of the GLC compared to conventional HRTM method and elemental mapping with this technique. Okay, so to be honest, the graphene liquid cell, the resolution should be lower than the conventional solid electron microscope, because there is a liquid layer which incorporates a lot of thickness related contrast and aberration to your sample. But still we can achieve several angstrom of resolution. So I did not include that slide in this presentation, but we can easily achieve 1.4 or 1.5 angstrom in the FFT information limit and the diffraction with the GLC. And elemental mapping with this technique, I think I have one in the previous slide, maybe. Yeah, if you see this closely, this is a LP-TEM image of the GLC map. You can both do the EDS and the EOS LP-TEM for visualizing the elemental mapping with the graphene liquid cell.
Hi, this is Dieter Isheim. I had a question, how important and how difficult it is to really get a single graphene layer at the top and at the bottom. Mm-hmm. And are there any studies like what happens if you have 2, 5, 10 graphene layers in a stack? And if there is any investigations in that direction, how thick can the graphene be until you run into other problems like handling it or not being too electron transparent anymore? So how many layers of graphene can you have at the top or do you have at the top and the bottom?
For this specific method, we are using just a single layer graphene prepared on the copper foil with the CVD method. But for other types of graphene liquid cell, which is MEMS-based one, we frequently use 3 layers graphene on the top and the bottom. So we can see the diffraction and confirm that there is a 3 layer on the top and 3 layer on the bottom. But with the 3 layer, it is the thickness would be around 1 nanometer, but there is not so many effect on the resolution at that time. But for more than 3 layer, currently I have no data, and other publication reported that they have used more than a 3 layer graphene to the graphene liquid cell. But I think less than 5 layer would be okay with the graphene liquid cell.
Thank you. That is very helpful. I did have another question. Mm-hmm. Is there anything known about problems with the graphene encapsulation depending on the voltage of the electron beam? Obviously, if you're looking at an organic material or something, you want to keep the voltage probably low. But what is the e-beam voltage, the acceleration voltage typically used for this type of microscopies?
So in terms of imaging with the TEM, acceleration voltage, if we are using high electron volt energy, we got more transmission and the contrast will be minimized. But if you are using the small low electron voltage, the transmission will be reduced, but the contrast will be increased. So one thing is the contrast. So we normally use somewhere between 200 or 300. That is just okay with the TEM. But if you go with the one mega electron volt, then it will be very hard to see some contrast in the GLC. Also, if we are using lower kV, too low kV, of course we can get a higher contrast, but chance of radiolysis will be increased. So, the cross section of the reaction will be increased at the lower kV. So we'll induce a lot of radical induced damage and intervention of reaction inside of the TM. So normally we use 200 or 300 for the liquid cell.
Ah, thank you. Mm-hmm.
Okay, I think we're done then. Thank you everyone for attending. If you want to reach out to Kunmo, his email is here and it's also on our website, and we'll be happy to answer any more questions. The video will also be up on our YouTube channel. Thank you.
Thank you.
Thank you.